ionic bond given by Kossel. The strong Coulombic electrostatic force of attraction between the oppositely charged ions, that is cation and anion, is called ionic bond given by Kossel. So, to have ionic bond, the condition is cation is must, anion is must. Between these two oppositely charged ions, strong Coulombic electrostatic force of attraction is so called ionic bond. Let us study the conditions favorable for formation of cation as well anion. Formation of cation. So, 1. Sir, this cesium is saying, sir, you can ask me, I will tell all the conditions which are favoring formation of cation. Cesium, the element, readily forms cation. Hence, what are all the factors, properties exhibited by cesium are favorable conditions for the formation of cation. Cesium, large atomic size, it is 1, 2, 3, 4, 5, 6s1. Cesium, low ionization energy. To remove this electron, required energy is very low, ionization energy is low. Cesium, high electropositive nature, it readily donates electron. And cesium, 55 atomic number, by giving out one electron, 55 minus 1, it gets 54 stable noble octet xenon configuration. Hence, cesium readily forms cation. It means the elements having large atomic size, high electropositive nature, low ionization energy, tendency to get noble gas, that is octet configuration, they readily form cation. These are the favorable conditions for the formation of cation. Similarly, anion. So, element always exists as anion is fluoride, hence fluorine, because of its small atomic size, high electronegativity, tendency to get noble gas configuration by gaining one electron. These conditions favor the formation of anion. Best example, fluoride ion, fluorine taking one electron, fluoride ion, cesium giving one electron, cesium cation. So, between cesium cation and fluoride anion, strong Coulombic electrostatic force of attraction, so called ionic bond. Hence, ionic bond is formed between the more electropositive metal like cesium and the more electronegative non-metal like fluorine. Readily forms cation, readily forms anion, we have ionic bond. That is, from cesium to fluorine, transfer of electron, that is cesium gives electron forming cation, fluorine takes electron forms anion, and between these two oppositely charged ions, cation and anion, we have ionic bond. In a nutshell, ionic bond is favored by large cation and small anion. For example, cesium fluoride, cesium chloride, cesium bromide, cesium iodide. So, here we have strong ionic bond. As atomic size increases from fluorine to chlorine to bromine to iodine, ionic nature decreases. CSF strong ionic nature, CSI weak ionic nature. Similarly, from lithium to sodium, potassium, rubidium, cesium. So, here lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, cesium fluoride. As cesium, so from lithium to cesium, cationic size increases. Hence, cesium ion is large cation. Large cations favors ionic bond. Hence, from lithium fluoride to cesium fluoride, ionic nature increases. Similarly, from lithium fluoride, lithium chloride, lithium bromide and lithium iodide. From fluorine to iodine, as anion size increases, as iodide is large anion, so lithium iodide is almost weak ionic nature, whereas lithium fluoride comparatively strong ionic nature. That is, from lithium fluoride to lithium iodide, ionic nature decreases. Properties of ionic compounds. The most common example for ionic compound is NaCl. By discussing NaCl properties, definitely we will be having understanding about properties of ionic compounds. So we know NaCl, it is a solid, hence ionic compounds are solids due to the presence of strong Coulombic electrostatic force of attraction, and also results in high melting points and high boiling points. For example, NaCl, its solid, its melting point is 820 degrees centigrade. Then only it becomes liquid or molten or fused, high melting point. Then NaCl, ionic compound, positive pole, negative pole, polar in nature. Ionic compounds are polar in nature, hence water, H plus OH minus, polar in nature. Hence polar substances, that is ionic compounds, are soluble in polar water. That is based on like dissolves like. Na plus is attracted by OH minus, Cl minus is attracted by H plus, results in solubility. Ionic compounds in solid state, no ionization, no free ions, because they are held by strong Coulombic electrostatic force of attraction. Hence, no ions, no conduction. In solid state, ionic compounds do not conduct electricity. They do not act as conductors. NaCl, solid, does not conduct, but on heating to its melting point, it becomes liquid, molten, fused. Liquid, molten, fused NaCl readily ionizes and gives Na plus ion, Cl minus ion. Na plus ion, cation, reaches cathode, undergoes reduction, addition of electron, gives sodium metal. Chloride ion, anion, reaches anode, undergoes oxidation, gives electron and chlorine gas is produced. So, liquid, molten, fused NaCl acts as electrolyte. It means it gives ions, thereby conductivity. So, it is used in Down's process for the extraction of sodium metal and production of chlorine gas, in which liquid, molten, fused NaCl acts as electrolyte. Similarly, NaCl, when dissolved in water, aqueous solution, that is NaCl plus HOH, in aqueous solution, NaCl ionizes and gives Na plus Cl minus, and water ionizes gives H plus and OH minus. Hence, brine solution contains all these ions, results in conductivity. So, during electrolysis, here Na plus says to H plus, because H plus is having more discharge potential, losing charge. So, H plus cation reaches cathode, undergoes reduction, that is addition of electron, hydrogen gas is produced. And compared to OH minus, chloride ion having more discharge potential, hence as anion it reaches anode, undergoes oxidation, that is removal of electron, and chlorine gas is produced. And the left out Na plus and OH minus, they combine and give NaOH, caustic soda. Hence, brine solution on electrolysis, it gives sodium hydroxide, hydrogen gas and chlorine gas or the products, and the process are called Kastner-Kellner process and Nelson cell process for the production of chlorine gas, NaOH and hydrogen gas by the electrolysis of brine solution. Ionic compounds in aqueous solution, for example NaCl, exists as free ions. Hence, once AgNO3 solution is added, this Ag plus ion readily combines with Cl minus and forms a white precipitate of AgCl. This reaction occurs in no time. It means ionic compounds in aqueous solution, they give very fast reactions. And ionic bond, it is strong Coulombic electrostatic force of attraction, hence it is only attraction, hence ionic bond is directionless. Lattice energy. Lattice energy of a crystalline compound is defined as the amount of energy liberated when oppositely charged ions are brought together, which result in the formation of 1 mole of crystalline compound, is called lattice energy. For example, Na plus ion, Cl minus ion are brought together, results in the formation of 1 mole of crystalline sodium chloride. Energy is liberated. In the equation it is plus 788 kilojoules. Lattice energy U equal to minus 788 kilojoules per mole. Similarly, when 1 mole of crystalline compound is separated into ions, it requires energy, is also known as lattice energy. Hence, 1 mole of crystalline compound is formed and 1 mole of crystalline compound is separated. In both the cases, the energy required or liberated is called lattice energy. Smaller the ion, larger the lattice energy. Similarly, lattice energy U is directly proportional to the charge of the ions and also their product. So, more the charge of cation and anion and their product, the magnitude, then U is more. So, more charge, more product, then U is also more. Order of lattice energies. We have lithium fluoride, Li plus 1, fluoride minus 1. We have cesium fluoride, Cs plus 1, F minus 1. From lithium to cesium, the size of the ion increases, hence lattice energy decreases. From LiF to Li, here plus 1 minus 1, plus 1 minus 1. So, from fluoride to iodide, as size is increasing, lattice energy decreases. Then MgF2, CaF2. So, both are fluorides. Here Mg plus 2, Ca plus 2. Mg plus 2 size is less than Ca plus 2, its lattice energy is high. So, MgF2 is greater than CaF2. Likewise, MgO, in case of MgO, Mg carries plus 2, O carries minus 2. But in case of LiF, Li carries plus 1, F minus 1. The product Q1 into Q2, 2 into 2, 4 units. Q1 into Q2 equal to 4. Q1 into Q2, that is called 1 into 1, that is 1. So, more product charge, hence more lattice energy. Lattice energy of a crystalline compound cannot be measured directly since no free ions. Hence, it is measured indirectly by Born-Haber cycle, which depends on Hess's law of constant heat of summation. According to Hess's law of constant heat of summation, whether a chemical reaction occurs in one stage or the same chemical reaction, say A to C, C to D, D to B, that is finally A to B only. Say one direct step, it is in 3 steps, same reaction A to B. The resultant heat change in both the cases are same. That means it is constant. So, according to Hess's law of constant heat of summation, whether a reaction occurs in one stage, same reaction occurs in several stages, the heat change is constant. So, based on this one, thermochemical equations can be subjected to simple addition, subtraction, multiplication, division operations. Thereby, we can calculate lattice energies and heats of formation of compounds by using Hess's law of constant heat of summation.